Distributed dispatching in the parallel server model. Hi everyone, my name is Shai, and this is a joint work with Guy Goren and Yoram Moses from the Technion Israel Institute of Technology. Today, we will present our work on distributed load balancing. Let me start with a brief introduction to the parallel server model. Once an application is not sufficiently small, it can no longer be handled by a single server. In such a case, the practice is to take several servers and a dispatcher, also known as a load balancer, that among other functionalities distributes arriving client requests among the servers. We will usually model it like this. Here, we have a dispatcher and it divides entering jobs among a set of identical servers. Each server has its own FIFO queue where jobs are waiting for service. And this in fact is the standard parallel server model. To be more specific, we make the following standard assumptions. We assume a parallel server model that works in synchronized rounds, where in each round we have the following sequence of events. First, we have possible job arrivals at the dispatcher. Then, a dispatcher must immediately decide to which server its job is sent to and dispatch it to the selected destination. Lastly, each server performs work and possibly completes jobs. Completed jobs immediately leave the system. What makes the parallel server model a challenging task is that both job arrivals and servers' service rates are unknown stochastic processes. This is of course done with the intent to capture the somewhat unpredictable nature of load balancing systems. So what differentiates one load balancing algorithm from another? Well, when designing a load balancing algorithm, we need to make assumptions about what is the available information to the dispatcher and how the dispatcher uses this information. The parallel server model has been the target of many academic studies for decades. Let's briefly go over a few of the most well-known and widely used solutions. The simplest solution is random. A dispatcher sends its job to a randomly selected server. And while this approach is appealing due to its simplicity, it often results in poor load balancing, especially when the system operates at high loads. On the other end of the spectrum, we have the well-known join the shortest queue. In JSQ, the dispatcher sends each job to server with the currently shortest queue. Indeed, in the standard parallel server model, JSQ offers strong performance and strong theoretical guarantees. In some systems, the dispatcher does not have access to all queue lengths when a job arrives. In such a case, the power of D choices offers a significant improvement over random, even when D equals 2. In the power of D choices, when jobs arrive, the dispatcher randomly queries D servers and applies JSQ considering only the D sampled queues. While the standard parallel server model received a lot of attention in the literature, much less attention was given to the parallel server model with multiple dispatchers. Nevertheless, with the rapid increase in the size and volume of cloud services and data centers, architectures with multiple dispatchers are quickly becoming the norm. This is because a single dispatcher can no longer utilize a magnitude of servers, possibly in different locations. So how did this architectural shift affect the research of the parallel server model? Well, during recent years, there were several research works addressing the multiple dispatcher case. For example, join the idle queue that relies only on signals from idle servers was introduced in 2011. Some of the most recent works include the local shortest queue and the local estimation-driven policies that rely on local estimations of server states at the dispatchers. Indeed, in many cases, these solutions yielded a significant improvement to the multiple dispatcher case. However, they still all have in common that they share JSQ's centralized dispatching nature. The shared property of these solutions is that the dispatcher always sends its job to the best server it knows of. So what happens when we have a good server and different dispatchers that recognize it? You can imagine the dispatchers as ships flocking to this good server. Now imagine a scenario with multiple dispatchers, but only a few good servers. This might cause a herding phenomenon. The good server is targeted by many dispatchers, causing its queue to rapidly grow. This leads to long response times, and in severe cases, the server might even drop jobs. To put things plainly, herding is a clear threat to performance in the context of distributed load balancing. So is herding a phenomenon that every existing load balancing algorithm suffers from? Well, the answer is no. But existing solutions do rely on a lack of accurate information in order to mitigate herding. The power of D choices, for example, considers only D out of all possible servers. This prevents herding for small D values, since with high probability, different dispatchers examine different servers. But this comes at the cost of reduced performance, since many good servers may not be picked and therefore underutilized. Indeed, in current solutions, there usually exists a sweet spot in terms of available queuing information, where below this sweet spot the performance is poor due to insufficient information, and beyond the sweet spot the performance deteriorates due to herding. And this led to a misconception that less accurate information leads to better performance. Is it indeed the case that there is such a thing as too much information in the load balancing context? Well, there is, especially if your algorithm is oblivious to the existence of other dispatchers. The cause of this queue length information paradox is that previous works optimized the individual dispatcher decisions rather than optimizing the collective behavior of all dispatchers. And this resulted in what can be described as selfish behavior by the dispatchers that is somewhat alleviated when a dispatcher is fed with partial or inaccurate information. We find that in order to solve this paradox, the load balancing algorithm with multiple dispatchers requires a distributed system approach, and I'm delighted to pass the talk to Guy, who will present our solution.
I thank Shai for the great introduction to the topic of load balancing. And now let's briefly formalize the distributed problem at hand. In addition to the standard parallel server model definitions, we now have n dispatchers instead of a single one. The dispatchers cannot exchange messages with each other, and we require the dispatchers to act symmetrically in the sense that they all run the same protocol and treat all jobs per round equally. I remind you that a round starts with arrivals that are then immediately dispatched to the servers, and some service occurs at the servers before the round ends. Okay, so what do we want from our load balancing algorithms? There are two objectives that we target. One, the average time a job spends in the system. Two, tail response times. For example, if we're interested in the 99th delay percentile, it means that we're interested in the response time of the slowest 1% of jobs. This measure is very important for client experience because a client request might be split into many jobs, and the response time the client experiences is the response time of the last job to complete. For instance, in a system where a client request is broken into 1,000 jobs, it is a common thing for a client to hit the 99.9 delay percentile. Let's look at this simple example with 5 server queues and the dispatcher. Assume the 2 jobs arrive at this dispatcher, then sending these jobs to the empty queue seems like a good load balancing decision. But what if we have a second dispatcher in the system with its own arrivals, or a third one with even more arrivals? Now using the same load balancing decision leads to all jobs herding towards the empty server, which severely increases the tail response of the last jobs at this server. Alternatively, dispatching the jobs completely at random will alleviate this, but at the expense of poor load balancing decisions. For instance, the empty server might end up with no jobs at all, which leads to wasting processing capacity. Evidently, the decisions of the dispatchers should be affected by the presence of other dispatchers in the system. In essence, we would like the combined decisions of all the dispatchers to reach a water filling effect, which can be viewed as a process of filling water into a container with an uneven bottom. Let's take a look at this illustration. We have the same scenario as before with the 6 arriving jobs. The result of water filling these arrivals is a water level of 2 3/4. In practice, even with a single dispatcher, such perfect water filling is not possible since a job cannot be split. Indeed, JSQ achieves the best water filling approximation for a single dispatcher. So, can we achieve an equivalent in the multi-dispatcher system? The answer is no, we cannot. But we can get pretty close. The key to achieving a water filling effect is coordination among the dispatchers. But dispatchers must make immediate and independent decisions at each round. We observe that while the dispatcher's decisions must be independent, the decision-making processes does not need to be independently optimized. Randomness is commonly used in distributed computing to break symmetry, and we use it as a means to allow coordination of the decision-making processes while maintaining the independency of the decisions themselves. We formalize multiple dispatcher load balancing as a stochastic optimization problem where our objective is to approximate a water filling effect. Giving the server queue lengths and the arrivals to the system, we want to obtain the probabilities by which a dispatcher should send its jobs to each server in order to minimize the expected L2 distance from the water level. This is a nonlinear constraint optimization problem, and we use the Karush-Kuhn-Tucker method to solve it. The solution has the following form, and we term it tidal water filling. Specifically, the probability by which a job is sent to server I depends on three things. One, the distance from I's queue to the water level. Two, the number of arrived jobs at the system. And three, how many other queues are below the water level. In the next few slides, we will provide some intuition to tidal water filling, how it achieves a water filling effect, and what the tidal stands for. Let's take a deeper look at our solution. When the number of arrivals and the number of queues below the water level tends to infinity, our solution obtains a simpler form. It approaches water filling in expectation. Namely, the probability by which each job is sent to a server is such that in expectation, we get exactly the water level. However, tidal water filling and water filling in expectation differ, because even in a large system, the number of servers below the water level may be small. Let's see a few toy examples to illustrate the intuition behind the tidal in tidal water filling. In this example, we have two servers. Server 1 has a single job in its queue and server 2 is empty. Assume that two jobs arrive at the system. JSQ results in both jobs deterministically sent to server 2. This is illustrated by the solid black line. In the case of water filling in expectation, the blue color shows the expected queue length. As the name suggests, this is exactly the water level, which is 1.5. However, this is only an expectation and not the actual result. In fact, this is not even possible, as one server must end up with at least two jobs. Moreover, there is a probability that both jobs will end up arriving to server 1, which is the worst possible outcome in this case. Tidal water filling, on the other hand, results in both jobs at server 2, just like JSQ, which is optimal for this case. Now consider the same scenario, but with 3 arrivals instead of 2. JSQ results in all jobs deterministically sent to server 2. Clearly, this leads to an imbalanced state. In the case of water filling in expectation and tidal water filling, the blue color shows the expected queue length. It is evident how the expected value of tidal water filling is uneven and creates a tide towards the better server, server 2. This lowers the probability for a severely unbalanced result in comparison to water filling in expectation. Essentially, tidal water filling adjusts the probabilities given by water filling in expectation in order to account for the fact that jobs are discrete and their number is finite. And the result is that we see water pushed towards the deeper server in something that might resemble a tie. Okay, so do we have everything that we need to execute tidal water filling? Almost. Recall that a dispatcher cannot communicate with other dispatchers, and thus it does not know their arrivals. On the positive side, we only need the sum of arrivals to employ tidal water filling. In our solution, a dispatcher approximates the sum of arrivals by multiplying its own number of arrivals by the number of dispatchers in the system. This simple approximation has an appealing property. The actual total arrivals equals exactly the average estimation by the dispatchers. Let's overview representative evaluation results. By standard practice, in all of our simulations, the number of arrived jobs at each round is independently drawn per dispatcher from a Poisson distribution. Likewise, the number of completed jobs at each round is drawn independently per server from a geometric distribution. Here, we see the simulation results for tidal water filling and 4 other algorithms: join the shortest queue, power of choice, join the idle queue, and local shortest queue. We do so over 2 different systems, one with 100 servers and 10 dispatchers, and the second with 200 servers instead of 100. We measure the mean job response time in rounds as a function of the load offered to the system. The offered load is the ratio between the expected arrivals and expected departures. It is evident how tidal water filling consistently offers the best performance, where the gap widens as the load increases. In these simulations, we examine the system at a challenging scenario of a high load of 99% of its capacity and measure the job delay tail distribution. Again, it is evident how tidal water filling consistently offers the best performance. For example, the 99.9 percentile, which can be viewed from corresponds to the 10 in the -4, in a system with 100 servers, tidal water filling offers an improvement of factor 2 over LSQ, which is the next best. For a larger system with 200 servers, the gap only widens. In our simulation, we found that other solutions switch leading places in different systems and different metrics. Tidal water filling, on the other hand, gives the best performance in both metrics and across all systems. We've seen that tidal water filling is the best policy for a setting with complete information of server queue length. But how does it perform with only partial information? You can find the details in the full paper. Here, we briefly overview representative results. The illustrated evaluation depicts a system with 100 servers and 10 dispatchers subject to a high load of 99% of the capacity. The figure shows the 99th percentile delay as a function of the percentage of servers that the dispatcher samples each round, which we denote as eta. To summarize our findings, tidal water filling only improves with the amount of available information, while other approaches have a specific sweet spot after which they deteriorate due to herding. There are other interesting things in the paper that are not discussed in this presentation, which is another reason why you should read the paper. We deal with unsplittable dispatching, which means a dispatcher must send the entire batch of jobs to the same server. This setting represents affinity constraints that apply to many systems. The analysis in this case is a bit more involved, but the resulting policy has a similar nature to that of the splittable case. In a setting of partial information, since tidal water filling benefits from more information, it is worth to consider non-distributed information gathering techniques in order to boost performance. We incorporate local views at the servers and use timestamps to make sense of the resulting abundance of available information. The paper also proves that our dispatching policies satisfy the theoretical stability guarantees, which are desired in the load balancing context. To conclude, the problem of load balancing with multiple dispatchers in the parallel server model is a real-world distributed systems problem. We believe that many more significant contributions can be made by applying distributed systems techniques. For example, how to better incorporate information gathering mechanisms. We were unable to fit our solutions to work well with sparse communication, how to deal with asynchrony in the system or heterogeneity of servers and dispatchers. There are many more questions left unanswered, and we discuss a few open problems in the paper. Thank you, and I hope you've enjoyed our presentation.